Welcome to the first plenary lecture of the afternoon. It gives me great pleasure to introduce Cheryl Prager. Cheryl did a DPhil at Oxford, finishing around 1973, and then she was a research fellow at ANU for 3 years till 1976, whereupon she accepted a lectureship at the University of Western Australia, rapidly rising through the ranks as senior lecturer professor, and most recently she won a Federation Fellowship, disproving the theorem that no mathematician has ever won one, but that they are extremely rare. Cheryl's initial field of research was permutation groups, which seems to be a well-trodden area, but in fact there's been quite a lot of exciting things. She finished a PhD just a few years before the classification theorem for finite simple groups, and so that threw up lots of interesting problems that could now be solved, and it also threw up many new problems. She also introduced rigour into the study of many questions where people thought they already knew the answers. Another major interest of Cheryl's is computational group theory, where she's made significant contributions to the problem of recognising classical groups through careful analysis of element distributions and other invariants. She also is a very distinguished combinatorial theorist, having made significant contributions to combinatorial design theory and algebraic graph theory. Algebraic graph theory is a study of graphs with a permutation action. Cheryl is a member of the Australian Academy of Science, former president of the Australian Mathematical Society, and has been on numerous boards, committees, and others too much to remember. Anyway, so I have great pleasure in welcoming Cheryl, who today will speak on regular permutation groups and Cayley graphs. Thank you, Cheryl.
Thank you very much, John. And I'd like first to congratulate those people who had the vision for holding this Congress, and then to thank them very much for allowing me to give one of these lectures. I very much appreciate that opportunity. I also like to thank the organisers, Gary and his crew. Especially Gary holds a dear spot in my heart as one of my students from University of Western Australia a long time ago. I think the organisers have done a really magnificent job. So thank you all. It's lucky that I have the chance to do this, isn't it? So perhaps I'm speaking on behalf of us at all. I chose as a topic for today's lecture something that I hope I will be able to communicate to a wide range of mathematicians in the audience. It's a mixture between my interests in combinatorics and in algebra. So let me see if I can... Oh, this is only a pointer. That's right. I have to do this. That one. Yes. Yes. So first, half of the title is about Cayley graphs. So what are Cayley graphs? Well, you start with a group, any group, G, and any set S of generators for G. And with that sort of information, the elements of the group are what we might call words in that generating set, just combinations of the generators, possibly with some inverses. So there's one word, ST, U inverse S. And the Cayley graph for G relative to S has got, as vertices, all the group elements. And we draw an edge from a group element B to another group element B times T, where T is one of the generators. So we don't tend to label the edges, but we usually will put an arrow on them, and you might notice that I've got one of the arrows wrong. You can see which one it is. So the identity element of the group will have arrows going out to each of the generating elements. I've only drawn a few of the edges. So that's a Cayley graph, and as I've just been describing it, the edges are determined by multiplication, and I'm deciding to have multiplication on the right by generating elements, by generators. Of course, since I get the arrows wrong, I usually like to have the generating set closed up under inverses, so throw in all the inverses, and in that case we would have edges going in either direction between any pair or no edges at all, and so we can forget about the arrows and regard this as just an ordinary undirected simple graph. And we'll call that the Cayley graph for G relative to S. Well, some reasonable questions like, it sounds fairly technical, where do they arise? Perhaps where do they arise in mathematics? Where do they come from? What kind of groups might give interesting Cayley graphs? And does it matter what the generating set is? And perhaps on the other hand, what sort of graphs come up as Cayley graphs if we build them out of groups? Are they important? Why? And what about the other half of my title? What's a regular permutation group? Well, I'll try to answer some of these questions as we go. Let's see how I go. Well, Cayley graphs do really arise all over the place in mathematics. One place is through topology, where a Cayley graph on a surface helps in maybe understanding properties of the surface, and topologists or algebraists will be interested in studying these things either from the point of view of knowing more about the surface or from the point of view of knowing what kinds of graphs can be embedded in the surface, or in particular what kind of Cayley graphs, and sometimes in trying to understand properties of the group from its embedding in various surfaces of various types. So there's a large amount of pure mathematics in this area that is involved with Cayley graphs. They also arise in perhaps a rather different way through computer networks, giving the structure underlying a lot of logical work in computer networks. Also in experimental layouts in some very well-structured designs of experiments in statistics that I've been involved with over the years. And a third place where we've heard some discussions through the plenary lectures this week is that very often Cayley graphs form a model for investigating a lot of different processes. So earlier this week we heard a talk from statistical mechanics about the Ising model, and there we saw some rather beautiful pictures of random walks on Cayley graphs. The Cayley graph forming the model on which one analyzes a Markov chain, and it forms the basis of percolation theory. But it arises all over the place, from that end right through to group computation. And so an area where I'm much more familiar is that latter one. If we start somewhere on a Cayley graph, perhaps even at the identity as I have here, and we make a random walk at every stage, choosing a random edge in which to exit that vertex, and we take about, say, n steps and end off at an element G in the group, we might ask the question, well, how random is that element that we end at? How many steps would we need to make in order for that element to be roughly uniformly distributed random element of the group? And if we continued to do that, how long a random walk would we need to make in order to be producing roughly independent, roughly uniformly distributed elements of the group? Now, turning that into defensible theory, into mathematics, was done by Babai in 1991, and that forms the basis for producing, at least in a theoretical way, uniformly distributed, approximately independent random elements for use in all of the modern randomized group algorithms. And the analysis of those algorithms is based on being able to make such random selections from groups. So Cayley graphs and random walks on them form the basis of a lot of theory underpinning the randomized computational group algorithms. But of course, they're graphs. And so Cayley graphs are interesting and important for studying group actions, and they're important in combinatorics and in geometry. And what I want to talk about in the lecture are, well, the other half of my title, regular permutation groups. I'd like perhaps to see some of this in a little bit of history over the last 100 years, talk a little bit about where Cayley graphs came from, the links through to group theory, and some rather recent work with some of my colleagues, which has relied on the finite simple group classification. So firstly, let's try to be all on the same page. Regular permutation group means, well, we've still got to decide we know and agree on what we mean by a permutation group. So we need a set, omega, and permutations on omega are just bijections from omega to itself. We put all of those permutations together and we get the symmetric group on omega, a large group under composition. And for that composition, I would take, say, this permutation G, which interchanges 1 and 2, fixes all the rest. Do that first, then do the next permutation, say 2, 3, which swaps 2 and 3, fixes all the other points. And that will mean, doing G first and then H, that will be my permutation G times H, which in the end, you can work it out, cycles 1 to 3 to 2 and back again. Okay, so that's the multiplication, which gives us this large symmetric group. And what I mean by a permutation group on omega is just any subgroup of the symmetric group, any subset of permutations closed under multiplication and inverses. And here's a little one which you'll see pictures of later. If I have the 5 points, 0, 1, 2, 3, 4, and I take the single 5 cycle that just cycles them around, take that as a generator for a group. So I use this notation. So angle brackets, I'm taking the group that I get by taking that permutation, repeating it as many times as possible. I'll get 5 permutations, and that will be a subgroup of the symmetric group on that 5-point set. Okay, so now over to regular permutation groups. What do I mean by saying a permutation group is regular? So let's take a permutation group G, subgroup of the symmetric group on omega. First, the concept of transitive. I'll say that this group is transitive if all the points are equivalent under the permutations in that group. It means take any 2 points, I can find a permutation in that group, takes the first point to the second. Well, regular permutation groups are essentially the smallest possible transitive permutation groups. Firstly, they have to be transitive, and secondly, if I look for a permutation in the group that fixes any given point, the only possibility is the identity permutation. In topology, I think maybe the word a free action might be used, and that's about the same, but in permutation groups or in group theory, we talk about regular permutation groups. The example I gave is a regular permutation group, and it could be interpreted in several different ways, using the cycle notation I wrote before in the first interpretation, or alternatively, I could think of it as the additions modulo 5, and I could think of the point set as being the integers modulo 5, or I could somehow or other visualize it by drawing the 4 points around here and thinking of it as the group of rotations of the regular 5-gon. So many ways of thinking about the same group and the same permutation group. But in fact, there's a very standard way to think about all regular permutation groups. So what do? Well, we take any group whatsoever, any group at all, and we take the point set omega to be the set of elements in the group. And this is starting to sound a bit like a Cayley graph, isn't it? So the point set, the points that we're acting on are the group elements. For every group element G, we can just take the multiplication on the right as a map from group element X with image X times G. So right multiplication gives us a map, gives us in fact a permutation of this set. And if we put all of those permutations together, it turns out that that is a subgroup, forms a group, I'll call it G sub R, R for right multiplication, forms a subgroup of the symmetric group on the set omega equals G. So it's a permutation group on itself, I guess, and it's pretty clearly isomorphic to the group we started with, and it's a regular permutation group. It's transitive and only the identity fixes the point. And moreover, every regular permutation group essentially arises like that. If we had the point set labelled nicely, and if we had the identification of the permutations with the group elements nicely organised. And of course, if we do it that way, and we think of the blobs being group elements, we could represent each single permutation by a diagram rather like the one that I showed on the first slide. If we take that a little bit further, if we had our favourite permutations, which are going to be the generating set for this group, and we represent each of the row sub G's for G a generator, then we're getting a picture of the Cayley graph if we use that visualization of a regular permutation group. And in a very strong sense, regular permutation groups are Cayley graphs, okay? Well, I think I've just got through here the process that one would go for, yes? You take your group, your generating set, you take your vertex set to be the group elements, you take the obvious things that we've been using as edges, and you form the Cayley graph. And when you do that, well, the nice thing is that right multiplication by group elements preserves the set of edges. That is, that all of these row sub G's in the group are actually automorphisms of the corresponding Cayley graph. And so Cayley graphs aren't just any old collection of graphs. They are, in particular, vertex-transitive graphs. So they're pretty nice graphs. They're all vertex-transitive. And if we do this with the standard example I've been running with in the previous slides, take the group of integers modulo 5. In the picture that I drew, I now want you to think of, say, number 1 as representing the group element add 1, okay? And I'm thinking that this is my group, that my generating set is going to be 1 and 4, which is, of course, closed under inverse, because if I add 4, it's the same as adding minus 1. So if I add 1 and then add 4, I'm adding 5, but not 5, that's 0, yeah? So this is 4 is the inverse of 1. And 0 is my identity of the group, and the edges that go from 0 should go to the generators, 1 and 4. And so this is my Cayley graph for this group using the natural generating set 1 and 4. And of course we notice that we've drawn the graph very nicely. We've only got half of the automorphisms. We've got the rotations which come from the Cayley graph, the construction of the Cayley graph, but we don't pick up the additional 5 reflections that you get for that graph. And so knowing that we've got a Cayley graph tells us something about the graph. It tells us that its group is vertex transitive, but it doesn't tell you everything about the graph. So let's go to a bit of theory, a bit of history. They're named after Arthur Cayley. He was a British mathematician, but first, in fact, he was a lawyer. He worked as a lawyer for 14 years in London, and only then did he accept a position as the Sadlerian Professor in Mathematics in Cambridge. He published 900 mathematical papers and notes. He's more famous, I guess, for his work on matrices in quantum mechanics, but he also worked in geometry and group theory. In algebra, you learn about Cayley tables. That's probably to be found in his work. I doubt if he really constructed. He certainly didn't name Cayley graphs, but they're named after him. So what I want to talk about is the problem of knowing whether you've got a Cayley graph when one is given to you. Now that's like a problem from combinatorics. It might also arise in other circumstances, but I want to explain through an example in particular what that problem really is. And then I'm going to spend quite a bit of time talking about primitive Cayley graphs. I'll tell you what they are, and tell you about the group theoretic work that goes back 100 years, which was related to them, but I will be speaking in a rather anachronistic way because that work was never couched in the terms of Cayley graphs. But I think it's easier to explain them if I use that language. And then I'll jump forward and talk more about the more recent work that I've been associated with. Okay, so what is the problem? How come we might not know if we've got a Cayley graph? After all, I explained to you what they were, and you can imagine every element, every vertex is labelled by a group element and the edges are all nice. If that's the case, then you know you've got a Cayley graph. But the graph might not come with that nice labelling. So there's a wonderful, almost romantic story about this particular graph, the Higman-Sims graph. It's named after Donald Higman on the left. Oh, sorry, the picture's a little bit dark, but that's Donald Higman, who died only a few years ago, and Charlie Sims on the right. And it's a very famous graph because it underlies a construction or a discovery of one of the sporadic simple groups in 1967, before and after dinner at Oxford during some conference. I mean, it just happened overnight, I think. Now, to explain a little bit what this graph was and how they discovered it, it's got 100 vertices. And the way to think of the vertices is to pick one of them, put it on one side, and then that vertex is joined to 22 others, so we put them in the next ball, and it's not joined to 77 others, okay? So it's 1 plus 22 plus 77. Now the way they discovered this graph, and in fact, they were not the first to construct it, but they didn't know. It appears in a PhD thesis of a student, PhD student from the University of Michigan, Mesner, but Mesner didn't look at the symmetries of the graph. So the way that Donald and Charlie constructed this graph was that they thought of these 22 points as the points of a Witt-Steiner system, a Witt design, and the 77 as the blocks of the design. And each block contains 6 points. And so they joined up the point type vertices with the block type vertices if the point belongs to the block. And so that gave them all these edges here. And the new point that they added in, that was joined over here. And somehow they had to invent some way of deciding when 2 of the 77 points were joined to each other. They did, and they did it very nicely, so that they knew for a start that all of the symmetries of this design, which was a sporadic Mathieu group, were admitted as automorphisms of the graph. And then they found some more automorphisms of the graph, and lo and behold, they constructed a new finite simple group, the Higman-Sims simple group. And the graph has, I think, automorphism group equal to the automorphism group of the Higman-Sims simple group. So they found this wonderful graph. They found the wonderful group. It was a very beautiful group. It was new. Found in this way. Turns out, and it is not obvious, that this graph is a Cayley graph for a rather small group of order 100. And the fact that it's a Cayley graph would not have helped them to construct the graph or the group. So in some sense, it wasn't relevant, nor is it obvious whether or not that graph was a Cayley graph, even though they knew the full automorphism group of the graph. It was a new group. They didn't know much about its subgroups, except the one they used to construct it. So it's not obvious sometimes that a graph is a Cayley graph, and sometimes it's because it's got too many automorphisms to sift through them and discover. So what is the problem, and what can we do about solving it? If the automorphism group of the graph is much larger than the group that we use to construct the Cayley graph, the construction that we used for the graph might actually hide the fact, as in that example, might hide the fact that gamma is a Cayley graph. So how do we decide? Well, there's a characterization which perhaps was first thought of by Lotzi Babai, but it's this one, and it's not difficult to prove. I won't prove it to you. If you're given a graph, let's say you're given a vertex-transitive graph, because Cayley graphs are vertex-transitive. So if you're given a vertex-transitive graph, it will be a Cayley graph if and only if there is a subgroup of the automorphism group that is regular as a permutation group on the vertex set. And if there exists such a subgroup, then the graph is isomorphic to a Cayley graph for that group, but some set of generators if the graph's connected. It is in fact possible for the same graph to be a Cayley graph of different groups. Not nice, but possible. And there's the obvious question that one should look at first is this a vacuous question amongst all vertex-transitive graphs? And it's maybe in some sense not so hard to decide if a graph's vertex-transitive. I'm not sure if that's true or not. Not all vertex-transitive graphs are Cayley graphs. The smallest one that is vertex-transitive and not Cayley is the Peterson graph, very famous graph, and that's a picture of it. So there is a problem there. Now, computationally, one might say, well, how do we carry this out by deciding, you're trying to find out if a graph, vertex-transitive graph, is a Cayley graph? Well, it's a bit like a recipe for soup or something. You first find the automorphism group, and then you look inside of it and see if there are any subgroups which are regular on vertices. Now, both of those steps are computationally rather difficult, non-trivial. I mean, finding the automorphism group of a graph, well, it's still undecided whether that's, or exactly what its complexity is. It's less than exponential, but there's no really fast algorithms for doing that. So they're both rather difficult problems. On the other hand, let me tell you about some empirical evidence and suggestions that we've got here. It seems from enumerations of small order vertex-transitive graphs that a high proportion of them are Cayley graphs. And these enumerations have been done up to, I don't know now, into the 30s. So it's not a great deal of evidence. But, for example, there are 15,506 vertex-transitive graphs up to isomorphism with 24 vertices. And of that number, 15,394 are Cayley graphs. So, and that's not atypical. And so there is a suggestion, Brendan McKay and I, that this might be true. He's braver than I. We've made it a conjecture, but I have no idea how or if this would ever be proved or disproved. If we pick a number n, and we look at the number of Cayley graphs on at most n vertices, divide it by the number of vertex-transitive graphs on at most n vertices, then we think that this should be approaching 1 as n gets large. So Cayley graphs should be pretty common, we think, amongst the vertex-transitive graphs. There's been a lot of different reasons for studying them, even within algebra. And there are various, quite a number of different directions in which the study of Cayley graphs has taken. And I want to mention just a couple of them, and the third one is the one that I'm going to follow for the rest of the lecture. But there's quite a large number of papers written about the so-called non-Cayley project. It is true that for some integers n, every vertex-transitive graph with n vertices is a Cayley graph. So you want to know what are those integers n? Or, turning it around, you might want to know what are the integers n for which there exists a vertex-transitive graph that is not a Cayley graph. And a slide a few back, I just showed you that the smallest such integer is n equals 10, and the example of the Peterson graph would be proving that there was a vertex-transitive non-Cayley graph on 10 vertices. So there's a lot of people that have looked at that, starting with a question by Dragan Marusic in the early 80s. Oh, there are infinitely many. So for if n is a prime, then all vertex-transitive graphs are Cayley graphs, for example, or prime squared, or prime cubed, but not prime to the fourth. Yeah. Okay. Yeah, so it's a funny kind of question, and you'll see maybe some more hints about why it's a funny question as we go on. Another Chinese mathematician, Mingyao Xu, suggested to study so-called Cayley graphs, normal Cayley graphs. Now, what would I mean by that? Well, it's rather hard, even if you knew the automorphism group of a graph, to decide whether it's a Cayley graph. That was that example of the Higman-Sims one I was perhaps suggesting that was a problem. On the other hand, if this group that you might use to build your Cayley graph happened to be a normal subgroup of the full automorphism group of the Cayley graph, then maybe it's not so difficult to decide. And really that is true, because the normalizer of this is not all that complicated, and you can kind of tell that the group is there if that group was a normal subgroup. And so Mingyao Xu termed these the normal Cayley graphs. And he would ask lots of questions, like maybe what kind of groups might you have such that all the Cayley graphs on that group would be normal Cayley graphs? Or what integers n might you have such that all Cayley graphs on n vertices would be normal Cayley graphs? So that's another direction that you might follow. Third one is the primitive Cayley graphs. Now I need to explain what they are, and I should have had another picture, I suppose, so let me see if I can do it with my hands. What do I mean by a primitive Cayley graph? Okay, sometimes, given a group acting on a set, like the automorphism group acting on the set of vertices, you can partition the set into blocks in a way such that every permutation in the group just permutes the blocks of that partition blockwise. And we say that that partition is invariant under the action of that group. Now, if we've got the set being the vertex set of a Cayley graph, then any such partition would in particular be invariant under the action of the right multiplications by the group elements, these guys. And the only invariant partitions for the regular action of this group G is a partition that you get by choosing a subgroup of G and taking its cosets. Remember that the set is labelled by the elements of the group. So you take the set, which is the subgroup, and you take all the right cosets of that subgroup, and then obviously by right multiplication just permuting around the right cosets. And they are the only invariant partitions under the action of the regular group G. Now, many Cayley graphs have got more symmetry than just that group. And if you've got enough elements, enough additional automorphisms to break every single one of those invariant partitions so that you've got no invariant partitions left, then we'll say that the graph is a primitive Cayley graph. So primitive Cayley graphs have got to have much larger, we think, well, in general, much larger automorphism groups than the group that you start with. And these are the ones which have received a lot of attention, both as a problem in Cayley graphs and also as a fundamental problem in permutation group theory. And so that's what I would like to tell you about, perhaps historically, to link this with perhaps the origin of permutation group theory, going back 100 years. So primitive Cayley graphs, the sorts of questions we are interested in would be for what groups, maybe? Yeah, for what groups does there exist a primitive Cayley graph on the group G? And the answer to that one's really easy. For every group, there is a primitive Cayley graph. And it's a really silly graph. So you take your group, you take the set of non-identity elements of the group, call that S. That is, everything is a generator except the identity, okay? That's your generating set. That will definitely be a generating set, right? And then you form that Cayley graph, and then you've got every single pair of elements joined by an edge, so it's a complete graph. The full automorphism group of the complete graph is the full symmetric group, and that's definitely primitive. So you always get at least one primitive Cayley graph for every group. But of course you get some rather interesting other primitive Cayley graphs. The Higman-Sims graph that I described to you, that's a rather non-trivial primitive Cayley graph for that small group of order 100. So I would like to tell in a very anachronistic way, tell you about a result that's about 100 years old by William Burnside. William Burnside was a British mathematician, English mathematician. He published in 1897 the first book in English about group theory. In 1911, he proved this result, but that's not the language he would use to state it in. So my language, the way I'm telling you today, is that 1911, there would be a proof of this fact. If you take a cyclic group, that's one where you just have to put a single generator, or maybe the generator and its inverse if you want undirected graphs. You take a cyclic group of prime power order, but not prime, okay? E to the m. And then Burnside essentially proved that the only primitive Cayley graph for that group is the complete graph. Now, let me state that again and then explain exactly what he proved. And then I hope you'll agree that what I just said is nicer than Burnside's statement. So what Burnside did, so that's my statement of Burnside's result. What his statement was that you take this cyclic group of prime power order but not prime, and he proved that if you look at the associated regular permutation group, yeah, the right multiplications by that group there, and if you take a bigger subgroup of the symmetric group, that the only strictly larger subgroups are two transitive. Okay, so what's two transitive? Two transitive means that all ordered point pairs are equivalent under the action of the group. So if we think about my other statement up here, if we take any larger group H, we can build, in fact, a graph from that group with H contained in its automorphism group. You have to just accept that that's the case. And if we had a primitive automorphism group sitting here, and we know from Burnside's result that it's two transitive, what do we know about the graph? Well, we know that if there was an edge for this with this ordered pair, then we can take this ordered pair of vertices over to our favourite ordered pair, and so there'll have to be edges everywhere in the graph. The graph will just have to be complete. So I'm going to use this sort of Cayley graph language to talk about some of the group theoretic results from 100 years ago. But there's one reason for telling you about two transitive groups, that it turns out that there's intense interest in two transitive groups. Right from the word go. I mean, 100 years ago, people were interested in them because they found some interesting examples and it started telling them a bit about group theory. And then in the 60s and 70s, again, a flurry of intense interest in them because it was via two transitive permutation groups that many of the new finite simple groups were discovered in those days. So there was a lot of interest in two transitive groups. Now, Burnside's result was about cyclic groups, and cyclic groups of prime power order. And there's a beautiful result by the German mathematician Ise Schur in 1933, where he extended that and showed that you get the same result if you just allow cyclic group of any order at all, but not prime, because the result isn't true for the prime case. So if you take any cyclic group of order n, where n is not prime, then Ise Schur proved that the only primitive Cayley graphs are the complete graph. on the set of points. Now, what's really important about this is the methodology. To do that, Ise-Schur developed a theory of what's now called Schur rings or S rings in honor of Schur. And those S rings were developed further and they sort of underlie modern theories of association schemes, of coherent configurations, of centralizer algebras, and even going through to Hecker algebras, which are the basis of a lot of representation theory. So it was a very important piece of work, but it was motivated by trying to understand these Cayley graphs in group theory. There was quite a lot of interest in this result of Burnside's and in further results. Now, what Burnside did was to publish a result with a mistake in it, and maybe it was this, maybe Schur knew about the mistake, I don't really know. But in 1922 or 1921, Burnside published a generalization of his result. He said, well, if I have a group that's abelian but not elementary abelian, then the same thing should be true. The only primitive Cayley graphs are the complete graph. But there was an error. Certainly the error was pointed out in print in 1936 by Dorothy Manning, but Schur must have known about it. I mean, this is a more general result than Schur's result, so why would he be publishing the same thing 12 years later? I don't quite know the history there well enough. But Wieland, another German mathematician, in 1935 was working in Berlin, so he knew of Ise-Schur's work, and he extended Schur's results to a certain class of abelian groups and then dihedral groups, and was so caught up with this theory that he decided to give a name to all the groups for which the only primitive Cayley graphs was a complete graph, and he called them B groups in honor of Burnside. And in Wieland's little book on permutation group theory, there's a whole chapter related to the theory of B groups and asking questions about what groups are B groups, what are the groups for which the only primitive Cayley graphs are the complete graph. And so from these results, we know quite a number of groups of B groups amongst the abelian groups, the cyclic groups, and all the dihedral groups. And this is a picture of Helmut Wieland. He's really the father of fairly modern, well, 20th century permutation group theory. This is a quote of an interview with him. He was concerned that the focus had gone on to abstract group theory to such an extent that many of the important results were being forgotten. And I guess that led to him publishing his book, which was published in English in 1964, Finite Permutation Groups, and has been extremely influential. It's certainly the book that I and many subsequent students, all around the world have used to learn about permutation groups up until the 80s, 90s, when we had the finite simple group classification. Then the world changed. But back to Wieland's theory of B groups. How am I going with time? Whoops, I should. As I said, when he proposed this study, there was intense interest on trying to find new finite simple groups. So there was a lot of work devoted to it. And the question was looking at the groups for which that you would have this property that all the bigger groups would be too transitive. That's the way in which that research was focused. Whereas these days, what we're interested in would be the primitive permutation groups themselves and the graphs on which they act. And we would be asking which are those primitive permutation groups that contain regular subgroups, or which are those primitive permutation groups that become automorphism groups of Cayley graphs. It's those kinds of questions that we're interested in. And so we might say what we're looking for are these Wieland triples. So a Wieland triple will be a group G, an overgroup H, and a set omega, so that G is a regular permutation group on omega, H is a larger group that is primitive, but it is not too transitive. Okay, if it were too transitive, the graph you would get out would be the complete graph. So we don't want that. So that's these triples that we're interested in. Every Wieland triple will yield at least one primitive Cayley graph, and every primitive Cayley graph will yield at least one Wieland triple. So the aim is to understand both the groups and also the graphs, perhaps depending on who you are, if you're an algebraist or a combinatorist. And in fact, there are applications of these outside of group theory and combinatorics into at least other areas of algebra. The problem's not new, the methods are new. As an example of what one could do before the classification, finite simple group classification, in 1935, American mathematician Miller published a paper where he was looking at primitive actions of finite alternating groups. And in his paper, he gave some, in my terminology, some examples of Wieland triples with this little group H being a finite alternating group. And he also gave some examples of numbers n for which there were no such triples. Okay, so just examples. Whereas in 1980, this is before the really before the classification, they're not using any deep theory, but just very significant work. Jim Weigold and Alan Williamson classified all the Wieland triples where this group H was the alternating or the symmetric group. I'd like to mention another result which was proved just on the verge of the classification and using the finite simple group classification, which does then yield some very funny sort of insight into these questions. It was proved by Peter Cameron, Peter Neumann, and one of their master's students, David Teague. And unfortunately, I don't have a picture of David Teague. So it's Cameron on the left, Neumann on the right, and gap for David Teague. They proved that for, in a sense, most integers n, and I mean there a subset of integers of density 1, not all but finitely many, not that sense of the word. The only primitive groups on the numbers 1 up to n are the alternating group of even permutations and the symmetric group. They're both too transitive. They don't give you any interesting primitive graphs or primitive groups. And so that would be saying to us that the set of integers n, and I'm afraid I left out a verb from this sentence, the set of integers n such that there exist no Wieland triples with the group G of order n, that set has density 1 in the natural numbers. So the things we're looking for are in some sense rare. There's still infinitely many of them, but they're in some sense rare, the numbers n. And so am I allowed? I'm getting to the end of my talk and I haven't quite finished it. I've just been having too much of a good time. Yes. This was the work that I've done with my colleagues, Jan Saxel and Martin Liebeck. We set ourselves this problem in the 90s, and I think we've just about finished it now. We were halfway there in 2000 when a rather long paper showed us the following. We were able to prove the following. If we have a Wieland triple, what do we know about the group G and the primitive group H? Well, as far as the primitive group H is concerned, there are 3 possibilities. It might be of a type where it is actually clear that there definitely exists a regular subgroup. And we said quite a lot about the possibilities for the regular subgroup. That's type 1. Type 2 is the group H is an almost simple group. It is really just about a simple group. It's caught between a finite non-abelian simple group and its automorphism group. And the third case is that the H is, let's abbreviate it to product action. It's kind of built up in some way from the almost simple groups. So there are these 3 types. And type 2 and type 3, well, we would like to know exactly when they do have regular subgroups. So we're not saying that every group of this type has one, and that's not true. And the case 2, we have now resolved, and I keep having different dates on it. I'm hoping that the memoir will appear this year so we can be done with it and have a single date attached to it. And case 3 is still open, but we've got some ideas. I'm working on that with some German mathematicians at the moment. Lots of things were done leading up to this and past that year 2000. Gareth Jones, British mathematician, 2002, he found all of the primitive groups in which there was a regular cyclic subgroup, so G being cyclic. Sai-Hung Lee, one of my colleagues, found all the primitive groups in which there was an abelian or dihedral regular subgroup. He was, although we're both interested in these because these sorts of groups and graphs are very important for embeddings as maps, as regular maps. And so they're more than a group theoretic interest in this. And in some sense, they complete the work of Burnside and Wieland and Schur in finding all of the automorphism groups of these graphs, or the primitive groups that can lie above such abelian and cyclic groups. There are various other results proved. I should mention in particular the work of Giudici and of Michael Giudici and Barbara Baumeister, where they essentially found all the Wieland triples for the group H being a sporadic almost simple group. It had been done for the alternating and symmetric groups. Barbara did this for the exceptional Lie type groups and a few of the classical groups, but it left the big, difficult case unsolved. And that is the case where the H was a primitive action of some almost simple, finite, classical group, the really difficult case. And that's the case that we had set ourselves to try to solve. I've pulled out all of my technical stuff, but the question could be translated into a classification problem of a certain kind of factorization of this group H. And we had available to us a tool that was very effective but quite difficult to use, which was the classification we had done in 1990 of the maximal factorizations of the almost simple groups. So using that, we did a lot of hard work, and along the way we had to produce a series of theorems that we hope will be useful for other people, for other problems, in working out for all actions of these classical groups on various kinds of subspaces, maybe non-singular spaces or singular spaces, exactly what are the possibilities for the transitive groups in those actions. And even with those theorems, there was a lot more hard work, and we obtained a complete list of all the primitive groups, primitive almost simple groups H that contain a regular subgroup, and all the types of regular subgroups that they contain. And it's a bit of a sad state of affairs that you have to do all this deep stuff and you don't know anything about the results until you've finished. So you finish it all, you've got the classification, and you have a look at it and you say, well, what does it tell us? And it's only by reflecting on the results that maybe you learn something. So the methods are just so deep that they're not really combinatorially helpful. So let me say some of the things that we learned. If we want to have a look and clear away all the sporadic stuff that happens for small values of n, so we just take values of n bigger than, say, 10 to the 32, and we say, well, what kind of groups arise as regular subgroups of almost simple primitive permutation groups? And the answer is, well, not many. I mean, surprisingly, not many. There's certain kinds of metacyclic groups, and there's these sort of affine type groups. And then there's a few groups which are kind of built out of certain kinds of alternating groups of particularly funny degrees, and nothing else. That's it. Really, it's a very strange classification that we came about. There's all sorts of stuff that happens with sporadic groups with small cases, but that's what happens asymptotically. What else did we find? Well, because we haven't been able to solve the product case yet, in certain cases we could handle that. So if we look for the Wieland triples where the group G is almost simple, then we could prove that either the group G had in fact itself to be a simple group, or there's one infinite family, and it's these symmetric groups, prime minus 2 degree, or there's two other groups, just two other groups. And in that case of these spectacular ones, which seem to be a little bit different if it's simple or one of these cases, inside of a Wieland triple, the kind of H's you get are some well understood ones where the group is simple, or a very, very short list. And so we found some strange stuff about these regular subgroups in primitive groups. What do we find out about Cayley graphs? Well, what kind of primitive Cayley graphs could we get? Well, I've already told you of one sort that you always get with every group. It's the complete graph. There is another sort. If you start off with a finite simple group, there's another kind of Cayley graph that's primitive that you always get. If you take S to be, say, an inverse closed union of conjugacy classes, then that Cayley graph will always be vertex-primitive, and we will understand its automorphism group pretty well. So there were two ways in which you could guarantee to get primitive Cayley graphs. Our theorem is that if the group is a non-abelian simple group and we have a vertex-primitive Cayley graph for it, then it's either one of these two ways arising, or the group is this kind of alternating group, a p squared minus 2, where p is 3 mod 4, and for each of those cases there's at least one primitive Cayley graph. Really strange. I should finish now. This is my penultimate slide. Yes, my penultimate slide. There was one curiosity. There's this group, the symmetric group on 5 points. It's got order 5 factorial, 120. And it came up as a regular subgroup in no less than 7 different classical groups. And, not all classical, are they? 7 different, almost simple primitive groups. And the relationships between all of these primitive subgroups are, on 120 points are shown in that diagram. And so those groups are giving us different information about different primitive Cayley graphs on 120 points, Cayley graphs for this S5. Very curious, but we didn't find things like that very often, not to that stage. So I think it's time for me to stop. Thank you for listening to me. I've really enjoyed myself. I tried to explain that Cayley graphs are very interesting objects and arise all over the place in mathematics. And my last part of my talk, I took a particular track through history, looking at them, at the class of graphs, the class of primitive Cayley graphs, from the point of view of graph theory, algebra, and combinatorics. We've got through to the primitive Cayley graph classifications using the finite simple group classification for the almost simple case, and we've still got this open, infuriating open case there, but we've got some good ideas, but there's still going to be a lot of hard work, maybe a few more years before we've cracked it. But hopefully that'll be the end. So thank you very much.
Does your classification give any more quantitative information about the density result? It seems to be proving that there are few in a rather strong sense.
Yes, we should look at it. It's really hard to do that, David, without knowing the full result for the product case. I mean, we should do that for the simple group case, and thank you for thinking of asking for it. But it would be an extremely interesting result to see whether we get even less numbers occurring for these primitive groups with regular subgroups. Because in the Cameron-Neumann-Teague result, they definitely got the first 2 or 3 terms in their density result. Very, very revealing, very interesting. And you could go further if it seemed helpful to compare what was happening in the Cayley graph case. Sorry, I don't know.
Any other questions? Oh, let's thank Cheryl once more.